Today, we're going to talk about a special kind of factoring. We're going to talk about how to factor a difference of squares. So we are on page 28 in your notes, and we're actually going to ignore most of what's on your notes page. So at the top of page 28, there's some information on how we can factor a difference of squares when we have, or using, I should say, the AC method. We're actually not going to use the AC method to factor these, what we would call difference of squares problems. They do need to be an even degree two-term problem, so that part still applies. And then I want to draw attention to the note up at the top. Even degree means that once I've taken out a GCF, I have an even degree for my function. So two terms, that's what we call a binomial. Binomial means two terms, and we want an even degree here. So an x squared and x to the fourth, something like that. The second example here does not look like an even degree binomial. It's a binomial because it's two terms, but if I pull out my GCF of x here, now I've got an even degree binomial. So this is the type of thing that we're talking about, even degree binomials. Two terms where my polynomial has an even degree. So again, I'm not going to use the AC method on these. If you're curious and you want to know how to factor these using the AC method, you can ask your teacher. But instead, I'm going to refer to this as a difference of squares problem. And here's why. These even degree two-term binomials that we're looking at are going to be of the form something squared minus something squared. So difference because we're dealing with subtraction, and then of squares because the things that we're subtracting are going to be perfect squares. Again, that's after we take out our GCF. So if we take a look at our first example here, 4x squared minus 9. Now this isn't written as something squared minus something squared, but 9 I know is 3 squared, 9's a perfect square. 4 is 2 squared, and x squared is x squared. So what I have here is a difference of perfect squares. Okay, so anytime I have a difference of perfect squares, my factored form is going to end up being the first term plus the second term, and then the first term minus the second term. So I get sort of this unique pattern that we can take advantage of for factoring a difference of squares. Now, if you read the notes, you'll see that we can use AC method here, and we end up using AC method with the same factored form. If I take advantage of that difference of squares pattern, our factoring is a lot faster and easier, particularly when I have a lead coefficient that's not 1 and a larger C value there. So we're going to factor using difference of squares here. So let's take a look at our problems down towards the bottom of page 28. 9x squared minus 4. So the first thing I want to do is identify what did I square for each of these things. So to get 9, I had to square 3. To get x squared, I had to square x. So this was 3x that I squared. To get 4, I had to square 2. Once I've identified what I squared for the first term and the last term, then I can write my factored form. So this would be 3x plus 2 times 3x minus 2. And remember, we can always check our work by distributing, and I'll do that here on this first problem. So 3x times 3x would be 9x squared minus 6x plus 6x minus 4. If I combine my like terms, my x terms are gone. I'm left with 9x squared minus 4. So there's my difference of squares factoring. For my next example, I've got x squared minus 81. So I want to know what did I square to get each of these pieces. To get x squared, I had to square x. To get 81, I had to square 9. So this is x squared minus 9 squared. That's my difference of squares. So now my factored form would be x plus 9 and x minus 9. For our next example, We have a GCF here. Both of these terms have an x, and 8 and 32 are both divisible by 8. So I can actually factor out 8x here as my GCF. Remember, I need to take out any common factors before I use my difference of squares pattern. So this would leave me with x squared minus 4. Now, inside parentheses here, I've got a difference of squares. This is x that's been squared, and this is 2 that's been squared. So this x squared minus 4 factors into x plus 2 times x minus 2. Don't forget to bring down your GCF. Our last example on page 28, we're going to work the same way. So I want to know, what did I square to get 16x to the 4th? Well, 16 is 4 squared, and x to the 4th would be x squared squared. Remember, power to a power, we would multiply. 2 times 2 would give me 4. So my first term was 4x squared that I squared. And my second term, what would I square to get 1? 1. So my factored form here would be 4x squared plus 1 times 4x squared minus 1. Now, if we take a look at the factors that I have here from this last example, these are, again, even degree binomials. 2 terms, even degree. Here we had odd degree because this is just the power of 1, that's the power of 1, this is the power of 1, power of 1, power of 1, power of 1. But here we've got x squared still. Now, we right now, based on the information that we currently have, can keep factoring this guy because this is a difference of squares, right? We've got that subtraction there. We can't right now factor this first piece anymore because it's not a difference of squares. We have a sum here. So we're going to leave this one alone for now, but we can keep factoring this guy. So what did I square to get 4x squared? Well, that would be 2 squared to get the 4, and then x squared to get x squared. And then to get the 1, we know we have to square 1. So I can keep factoring this into 2x plus 1 and 2x minus 1. And then we'll just bring down that first factor of 4x squared plus 1. And then just as a refresher, remember we can find the x-intercepts from factored form. So that's pretty easy on problems like this second example that we did. My x-intercepts would be -9 and +9. Here our x-intercepts would be 0, -2, and +2. Anytime I've got a number in front of x, remember that you can set that factor equal to 0 and solve for your x-intercept. So we get an x-intercept at -2/3. And then if you want to set equal to 0 and solve again for this guy, you can, or several of you noticed in class, we just change the sign on this and divide by that coefficient. So -2/3 and +2/3. For our last example, for right now, we're not going to get any x-intercepts from this. We'll talk more about this a little bit later on in our unit. But for these guys, we would get x-intercepts at -1/2 and +1/2. So that's factoring a difference of squares. Again, you need a binomial, 2 terms, even degree, and they must be perfect squares that you're subtracting to factor as a difference of squares. That's why we couldn't factor this guy anymore. Okay, so difference of squares. I need 2 terms, so it's called a binomial, and I need even degree. So the degree or the exponent I have, that biggest exponent needs to be an even number, difference of squares.